People say that Galileo climbed to the top of the Leaning Tower of Pisa, leaned out over the side, and dropped two balls, a heavy ball and a light ball. If you're like most people, you might guess that the heavy ball would fall faster. But in fact, Galileo reportedly observed that the two balls fell at the same rate. Why would they do that? What does it tell us about the relationship between how things move and how gravity affects them? That question inspired this short lecture, A Tale of Two Masses, in which we discover the surprising equivalence of gravitational and inertial mass. Actually, I might have also called this lecture A Tale of Two Laws because we need to start by looking at two fundamental laws of physics. To figure out the acceleration of each ball, we start with Newton's second law, F equals ma. That's force equals mass times acceleration. The mass in this law is called a body's inertial mass. The inertial mass is a measure of an object's resistance to having its velocity changed. So it tells you how hard it is to accelerate or decelerate a body. The larger the inertial mass is, the less the body accelerates for a given force. So if you take a mass, maybe a baseball, let me draw it here, let's pretend like that's a baseball, and you accelerate it with a given force, F, it will accelerate at some rate. Now, if you double the mass, maybe by packing putty in all around the outside of your baseball, and you accelerate it with the same force, it will accelerate at only half the rate. So to figure out the acceleration of any given test mass, it seems like we need to know the body's mass, and we also need to know the force that acted on it. So one of Newton's big ideas was that the force that makes things fall on Earth is the same force that makes the planets move around the sun. Any two masses attract each other with equal and opposite forces. I'll draw the masses as dots here, m1, m2, and the forces as arrows, F, F. And the law of universal gravitation tells us that these two masses attract each other with equal and opposite forces, and it also tells us the magnitude of the force, which is g m1 m2 over r squared. Here, F is the force, g is the gravitational constant, m1 is the body of the mass called 1, so you know what m2 is, the mass of the body called 2, and r is the distance between m1 and m2. So in this equation, we again have two constants, each of which is a property of one of the bodies that's involved in the equation. We also call this property of a body the mass. In this equation, it's the gravitational mass, and the gravitational mass is the property of a body that creates a response to the gravitational force between the body and another body. So if I took this mass up here and I doubled this mass, I will double the force that this mass feels being pulled towards the other mass, and I would also double the force that the other mass feels. Let's look at how the law of universal gravitation might create a force between two astronomical bodies, the Earth and the Moon. Here's a great photo of them as seen from space. So here's the Moon, and we'll call its mass m sub m. And here's the Earth, and we'll call its mass m sub e. And the distance between them we'll call r sub me. Notice on the last slide I used an arrow to indicate the force on the Moon and the force on the Earth, and here I'm using a double-sided arrow to indicate the distance between them. I could also draw the forces, and they would look like this. This is the force that the Earth exerts on the Moon, and this is the force that the Moon exerts on the Earth. Now that we've given all those constants a name, we can say that the force between the Moon and the Earth is g m sub e divided by r sub me squared. Now let's consider a test mass that's just above the surface of the Earth. So imagine we have a test mass very close to the surface of the Earth, like this little brown dot here. And we want to measure the attraction between this giant planet, Earth, and this tiny test mass. So again, we'll call the mass of the Earth m sub e, and now we'll just call the mass of the test mass little m without labeling it. The distance between the center of the Earth and the test mass is about the radius of the Earth, r sub e. So the force between them is F equals g m sub e divided by r sub e squared. Now we have the equation for the force on a particle very near or on the surface of the Earth. You'll notice that all the numbers on the right-hand side are constants except for the mass of our test mass. So we can group all of the constants like this, F equals little m times g m sub e divided by r sub e squared. We'll get tired of writing all these constants, so let's give the group of them their own name. Little g equals capital G m sub e divided by r sub e squared. The radius of the Earth is about 6 million miles. The mass of the Earth is about 6 times 10 to the 24th kilograms, and you can look up more precise values of those numbers and plug them in and find that little g is about 9.8 meters per second squared. Now we can rewrite this equation as being F equals mg. That's so important that I'm going to circle it in red pen, and we use that equation a lot when we're studying the dynamics of bodies near the surface of the Earth. So now let's go back to our original problem. A body falling near the surface of the Earth, and we want to know what its motion is. Here's the surface of the Earth. I draw that to indicate that that line represents the boundary of a solid region. And here's some test mass. And according to the law of universal gravitation, a test mass near the surface of the Earth feels a force towards its center of F equals mg. If I doubled the amount of mass, I would double the force towards the center of the Earth. But according to Newton's second law, the force on that body equals its mass times its acceleration, F equals ma. So we put these two equations together and we can write ma equals mg. Now, remember that this is the inertial mass and this is the gravitational mass. They didn't have to be the same, and for other forces, like electric forces, the mass of the particle has nothing to do with how big the force on it is. For electric forces, it's the charge that matters. The amazing thing is that these masses are the same, so they cancel. So you can see that if those are the same, then the acceleration of the test body will be a equals g, which is a constant independent of the mass. So you could do the same for any mass, and you would find that the acceleration g equals 9.8 meters per second squared for any body falling on the Earth, independent of its mass. The observation of Galileo that a heavy ball and a light ball fall at the same rate was the first indication that gravitational mass equals inertial mass, which is known as the equivalence principle. For more reading about the equivalence principle, I refer you to an excellent article in my favorite reference, Wikipedia. And some of the highlights of this article are Einstein's statement of the equivalence principle, a list of experiments that have tested the equivalence principle with ever-increasing accuracy, and some discussions of modern theoretical work on what might be the fundamental reasons behind the equivalence principle. By the way, I'm not sure, but I think that the measurements might have been made, not by Galileo himself, but by 2 graduate students. And since this is my story, I can say that their names were Apocrypheus and Godonkin.